In this tutorial, I'm going to explain what specific heat capacity is and how you can calculate it. Let's start with the definition, which is extremely hard to understand when it's just in words, so I'll give you some examples. Here's the definition. Specific heat is the amount or quantity of heat required to change the temperature of 1 gram of a substance by 1 degree Celsius. So let's look at silver. If you had a little hunk of silver, the specific heat of silver is 0.235 joules per gram times a degree Celsius. What that means is that if I started heating some silver, it would take 0.235 joules of energy before that gram nugget of silver's temperature rose a whole degree. What does that mean for the particles? It means that in order for me to make silver's particles move 1 degree faster, because remember, temperature is a speed, in order for me to get that silver to move 1 degree faster, I've got to give the silver 0.235 joules of energy. And that's for every gram of silver that I have. So the more silver I have, the more energy I need to raise the temperature. Same thing with aluminum, same thing with water. Notice that the two metals here, silver and aluminum, have much lower specific heat capacities than water does. Water is 4 point something, and silver and aluminum aren't even quite 1. What that means is that water actually takes a tremendous amount of energy to make its molecules move faster. For every gram of water, you need a little more than 4 joules of energy to get the water to raise its temperature 1 degree, and that's for every gram of water you have. And this explains why if you have a swimming pool full of water, it's going to take a lot longer to boil that water than it does to boil a cup of water on your stove, right? It's because more water takes more energy to speed up more molecules. Doesn't that make perfect sense? So specific heat really measures how hard it is to get your molecules to move faster. Now, what controls that? Well, the control on that is how attracted to each other your molecules are in the first place. We've talked about this before. We compared water to alcohol, and we noticed that water molecules are really clingy. They attract each other with a lot of power, and as a result, it's hard to get water molecules to move apart from each other. They cling together, so if you drop them onto a surface, water molecules bead up, alcohol particles not as much. If you boil them, the water will take a lot longer to boil than the alcohol will. The water will boil at 100 degrees, the alcohol will boil around 80 degrees. So water and alcohol have very different properties because of the attractions that their particles have for themselves. So water particles have this really strong polar attraction. They have lots of positive and negative charges in them, and that's what makes molecules of water so hard to move around. They cling to each other. So when you add heat energy to them, it takes a lot of heat energy to get them to move faster or move apart and change state. Silver and aluminum, even though they're solids at room temperature, and you might think, oh, they've got to have a stronger attraction between their particles than the water. They do, but there's a lot of freedom of motion in metals that allows the molecule between the individual atoms, that allows the atoms to sort of have this freedom that we don't expect in a solid. Believe it or not, most metals are kind of soft and bendable. We call this being malleable. And metals that you encounter usually have been contaminated deliberately with some other substance to make them harder. But when they first come out of the ground, metals are actually quite soft and movable. They're kind of like putty almost. Silver and aluminum are just, two examples, and both of them are really good at conducting heat. What does that mean? Well, it means that you wouldn't want to take a spoon made of aluminum and put it in hot soup, because if you did, pretty soon your hand would be burning. Instead, you're going to want to stir that soup with a wooden spoon, which doesn't have a very good ability to conduct heat. Both of those things have to do with heat capacity. Aluminum has such a small heat capacity that heat spreads through it really, really quickly. It's easy to make silver molecules move faster with heat energy. It's much harder to make wood molecules move faster with heat energy. As a result, we prefer using wooden spoons when we're cooking. You might eat your soup with a aluminum spoon or a silver spoon after it's come off the stove, but definitely not while it's on the stove. That would be dangerous. So that's what specific heat is. How do you calculate it? Well, here's the formula, and like all formulas, it uses letters to make things simpler, but when you first learn a formula, the letters don't mean anything to you, so you have to take a little bit of time to adjust to the letters. Q stands for heat added, or the amount of energy in joules that you're adding. So this is in joules. This is the amount of heat energy that you're adding. Specific heat is the amount of energy it takes, remember, to heat something up by 1 degree Celsius, 1 gram of it by 1 degree Celsius. So the units of specific heat are joules per gram times a degree Celsius. Those are really odd units. Remember, we learned about units like this type back when we did physics with the Newton, which is a kilogram meter per second squared, which is all weird. Mass is measured in grams, and the change in temperature is in degrees Celsius. Remember this symbol delta, which is a Greek letter that's used in math and science to mean the change in. It means change in. Okay, so in your experiment, you are first going to use the equation just like this. So you have to find Q. But you need to know Q of what? Well, you're trying to find the amount of heat energy absorbed by the water when the metal went into it. To do that, you're going to set your equation up as Q equals, you're going to put the heat capacity of water in here, which is given to you as 4.18. Don't forget your units, joules per gram times a degree Celsius. You got to multiply by the mass of your water. That's the water in the cup, right? That's the mass of the water, the tap water in your cup. You're going to multiply by that. And then you're going to multiply by the change in temperature that water went through. So in order to figure that out, you've got to get your starting temperature of the water and the ending temperature of the water. So you've got both of those and you have to subtract, and then you're going to do that change in temperature here. Make sure that's in degrees Celsius. So you multiply all that together and you should get a value for Q that will tell you in joules, that's the units you'll wind up with, in joules how much energy was absorbed by the water. After you have this number, you're going to use it in the next equation in number 4. Okay, now we want to find out the heat capacity, the specific heat capacity of our metal. To do that, we need to know how much energy in joules was absorbed by the water, which we just found out. So we're going to use that for our top number. So you're going to put your Q up top. Now you want to know what the mass of the metal is. This is the metal's mass. And the change in temperature is the same for the metal as it is for the water. You're going to put that in here. So you're going to divide the number we just found in the previous slide by the mass of your metal times the change in the metal's temperature. That'll give you your heat capacity of the metal. Don't forget that the units of your heat capacity are joules divided by grams times a degree Celsius, which are really weird units, but it's important that you write them correctly. That gives you your specific heat capacity of your metal. Now you can look up on the chart and see which one of the metals do you think you have based on the number you got. If your number doesn't even come close to matching something in the table, you might want to call me over to look and see if you did the work properly to calculate out your heat capacity. It's possible that you got confused about what units go where or about what numbers go where, and I would like to help you correct that if possible before you go any further. Okay, see you in the next tutorial.